Okay, so here we are to talk about chapter 3. This one is really dependent on your ability to name chemicals. So you want to master chapter 2 and then come to this chapter. The other thing we're going to learn about here, besides just writing reactions, which is the part that needs names, is a little bit of how we characterize the masses of different compounds. So it's important to be able to read a compound and put a compound together. So if I say iron 2 sulfate, you know that means FeSO4, because you need to know which atoms are in there before you can figure out the mass of things. Okay, so let's jump into it. First off, I like this quote from Antoine Lavoisier, who was one of the first chemists. He published the first chemistry book, and also was instrumental in designing the metric system, and also lost his head in the French Revolution. Oh, and also worked with his wife quite a lot. And so the pair of the two of them, he usually gets most of the credit, but the two of them were actually really important. And without her work, saving his records, his contribution would probably not have been as significant either. So anyway, he says this, and this is like a lot of really old, weird words, and it's translated from French. But he says, we may lay it down as an incontestable. Incontestable means you can't argue with it. Axiom, which means truth. So an inarguable truth is what he's saying here. That in all the operations of art and nature, so in other words, the universe, right? That's what we're talking about here. Nothing is created. An equal quantity of matter exists both before and after the experiment. So this is a way of rephrasing what we call the law of conservation of mass. However much you start with is what you end with. And this was not actually as intuitive as it sounds, because, like, say burning something. You take a log, you light it on fire, and it appears like the ash you have left over weighs less than the log you started with. And it does, because much of the products of combustion are vapors. They're gases. They, drift off in the wind. If, however, you captured all the gas particles that are produced and all the ash that's produced, and you put it all together, it will weigh as much as the log did to begin with. Okay, so that's what he's saying here. Now, when we're talking about molecules, right, you can't count individual molecules. So another scientist had to come along, and he was actually studying a lot of gases. But he figured out if you had a particular volume of gas, it had a certain number of particles. And he didn't really know what that number was at the time, but later on we assigned the phrase Avogadro's number once we could measure it, okay? And so essentially, Avogadro's number, which has the symbol capital N, subscript capital A, is a way of noting what a mole is worth. So 1 mole of anything is always worth 6.022 times 10 to the 23 of that thing. So if I say I have a mole of eggs, I have 6.022 times 10 to the 23 eggs. Pretty sure there's not that many eggs on the entire planet, but that's what I would have. This number comes from the number of carbon atoms, carbon-12 isotopes in particular, that are contained in 12 grams of carbon. So carbon is easy to isolate and relatively simple to isolate as just a pure isotope, meaning the whole sample is all carbon-12. And then the trick is to be able to count how many atoms are in there. And so we need some technology to do that, which we have now. Didn't have in Avogadro's day, or certainly didn't have in Lavoisier's day. But we can do it now, more or less. And we have actually a couple different ways of measuring this, and this number has been refined over the years. There's actually even more significant figures if you want to look on Wikipedia. And they have been verified through multiple different kinds of testing, so that, our method is not limiting our precision, and our method isn't going to limit our accuracy. So we're pretty sure about this number. And so we have decided to use the phrase mole. I have no idea why. It has nothing to do with the thing in your garden. But chemists need a way to talk about really large quantities of things that you can kind of handle, right? So writing out scientific notation every time you need to talk about an amount of chemicals would be really obnoxious. That's why Avogadro's number was invented. All right, and so here this picture shows 1 mole. So each one of these containers here, these are Petri dishes, which are about like, golly, 3 or so inches across, like, I don't know, about like that, and maybe 1/4 of an inch to 1/2 an inch deep. Petri dishes here are being used to hold 1 mole of several different substances. So table salt, sodium chloride. It doesn't even fill the container, right? So that's how much 6.022 times 10 to the 23rd particles of sodium chloride, that's the volume that it has. The mass is shown right here, 58.5 grams. Okay, so there we go. So that mass comes from the numbers on the periodic table, right? And so sodium chloride is NaCl, of course. And if you look, I think on our periodic table, it's on the upper left of each box. So here's like copper. So sodium is 22.98977. And chlorine is 35.453. So the way to figure out how much the entire, and again, those are weighted average based on the isotopes and the percent abundance of that element. They're an average of all the different sodiums in the world, in the universe actually. And that does get updated actually occasionally, not frequently for very well-known elements, but anyway, so I like to round to 2 decimal places. That's an arbitrary choice. But that unit is actually in terms of grams per mole. And chlorine is 35.45 grams per mole. So those numbers are right off the periodic table. And you just add them together, and that gives you the weight of the compound sodium chloride. So this is called a molar mass, okay? And we're going to practice those again. But right now, it's important to understand that different particles have different sizes. A sodium and a chlorine is relatively small. Iron 3 chloride, this orange pile, this is what we used in the trace contamination experiment. This is a bigger particle. Iron has a weight of 56, so it's a lot bigger. So, and then also you just have more atoms, right? FeCl3 has 4 atoms instead of 2. And so the weight of that is 270.3 grams in 1 mole. So you can either write that as an equality or you can write it as a fraction. And we don't always write the 1 mole on the bottom, but it's implied. Okay. So Avogadro's number allows us to go from, so obviously with 4 particles, each of them, you know, iron is bigger than sodium. That means that you're going to need a larger pile of particles. If each individual particle is bigger, the pile will be bigger, but it's the same number of particles, right? It's always 1 mole. So for iron 3 chloride, 1 mole is 270.3 grams, which is the same thing as saying 6.022 times 10 to the 23rd particles of iron chloride. Right, so each one of these is a mole of a different substance, so you can get a feel for roughly what it means to have 6.02 times 10 to the 23rd particles. Okay, I'm going to link this video. If you click on this picture in the presentation, it's actually a video. It's a little song that I want you to watch, and I have students that I taught like 5-6 years ago who come back and sing that song for me. But it helps you to understand what a mole is used for. And so sort of a textbook definition is that a mole is a unit that means this many of anything. You can apply it to anything. We usually mostly apply it to chemicals because that's the only thing, atoms, molecules, that's the only thing you would have so many of them that you need to use this kind of terminology. We use it a lot to convert between the particle level picture of what's there and what we call the macro level. So the particle level is, the number of particles that are there. And the macro level is ultimately grams. Okay, so that's how we're going to use it. So for example, if we want to know how many hydrogen atoms are present in a given amount, we can figure that out. And we're going to use dimensional analysis so much in Chapter 3. So here's our first shot at it. So it's not just for converting units, it's also really useful for converting between different models. So in chemistry, we have things on the particle level, things on the micro level, things on the macro level, and we also have symbolic representations like H2O, right? And so we're trying to learn these different domains and connecting them together. And so one thing that kind of threads through all of those different domains is using dimensional analysis to cancel units. Okay? So the first thing we have to do is calculate how much a water molecule weighs. All right, and this is where Avogadro's number is kind of folded into that. So first off, we have 2 hydrogens, and if you look at your periodic table, each hydrogen has a weight of 1.01. I'm rounding to 2 decimals. That's usually enough significant figures. If I'm doing really careful work, I might have to go look up some extra figures. But I have 2 of those, right? So I'll take that number and multiply it by 2. And I have 1 oxygen. Oxygen is 15.9994. So I'm going to round it to 16.00. I only have 1 oxygen, so I don't need to multiply it by anything. And then I just take these 2 and I add them together. So I would write it like this normally. And so we get 18.02 grams for every 1 mole of water. So that's about water. Okay, well, so if I wanted to figure how many grams, so we have different kinds of questions. Here's one. We'll come back to that. Here's another one. We can go, how many grams of water do we have? That's one kind of question. In that case, we're using the numbers off the periodic table to go from moles, which is the macro level, into something we can actually measure in the lab. And you're going to do it by just putting grams on top and moles on the bottom so they cancel. So if I needed to weigh out half a mole of water, I would weigh 9.01 grams of water. So that's one kind of question. This is the other kind of question, where we're going in the other direction. We're going from something that represents number of particles into the particle level, right? So we're going kind of up in scale, now we're going to go down to the smaller scale. All right, so we start with the same number. We're starting with that 0.50 moles of water, and now I'm going to use Avogadro's number as my conversion factor. So Avogadro's number defines what a mole is. In this case, it's going to be molecules of H2O is our unit on the top. That might be ions, it might be atoms if we're talking about an element. So you kind of can use whatever particle you're looking at as your unit on the top. And then on the bottom, it's just 1 mole. So this comes from our definition, right? We said 1 mole is the same thing as 6.022 times 10 to the 23 of whatever that thing is, right? And so now we can cancel moles. Now, this is a part where you need to be able to use your calculator correctly. So even if you think you understand this concept, I want you to get your calculator out and actually punch the numbers in and make sure you get it right. So the answer you're looking for is 3.011 times 10 to the 23rd. And the unit is molecules of water. You need to use a button that either says EXP or EE or a whole variety of things depending on your calculator. But you want to look up in your manual how to enter scientific notation.